In this video, we're going to show how we can invert differential operators, provided we apply appropriate boundary conditions. Over here on the left I have my text editor, and in the middle I have my MATLAB session. We'll start off by doing a one-dimensional example where we take a derivative in the x direction. Alright, so make a mesh points x equals... this time, to make things simple, I'll start off by making a mesh of equally spaced points with the spacing to be 1. So I'll set dx equal to 1. And I'll try to make the mesh small so we can actually look at the differential operators, see what they look like. So we'll start from x equals 0 by steps of dx up to 5. Like this. So let's run it, see what we have. Let me save it. And then my dx is 1, and my x variables goes from 0 to 5. The length of my mesh is, of course, 6, because of the 0 point. Alright, so now let's make our difference operator, and we'll use the same technique we used for the 2D operators that I showed in the previous video. It's a little bit overkill for a 1D mesh, but it works, so we'll use it anyway. So the first thing is we index all the points. So n would be equal to the length of x, and then ii is equal to 1 to n. And then to make the shift operators, I first have it in I east is equal to ii of 2 to n and 1. So we'll do a periodic shift, and I west is equal to ii and 1 through n minus 1, like that. Then I make an identity matrix, and then I permute the rows. I east is equal to I of I east, and I west is equal to I of I w. So let's look at what these operators look like. e.g. full I east. So it's the identity, but everything is shift over by 1, and similarly IW will be shifted the other way. Okay, so from this we can construct a finite difference operator. So let's do the backwards difference. BDX is equal to I minus I west, and then we divide by dx. In this case we're dividing by 1, so it's not particularly interesting, but later on we'll change that dx, so I just want to put it here. Alright, so let's run it. e.g. full BDX, and what we have is two bands, a band of 1s down the main diagonal and minus 1 in the minus 1 diagonal, because it's a backward difference. So here at the first point we have to reach over onto the eastern side to get the point, because we're assuming that it's like a cylinder, things are wrap around. Well, let's increase the dimensions and show that it really does do a derivative. So I'll put 0.1 f is equal to, let's say, x cubed, and the f analytical should be 3 times x squared. Sorry, not the f analytical, the df dx. And the df dx numerical would be equal to d dx times f. And let's compare those two. e.g. plot x comma df dx analytical, and hold on and plot x df dx numerical. Okay, so you can kind of see the blue and the orange curve, one on top of the other. Then the first point is messed up, and that's because the function I'm taking the derivative of is not a periodic function, assuming that my function is periodic. So that's why there's kind of a mess up at the beginning here. But otherwise it looks pretty good. If I zoom in, right, they're pretty close. And if I made the dx even finer, they would approach to each other even more. Okay, so, but now if I try to invert this operator, you would think that the inverse should be the integral. And what I get is, if I make it a full matrix, are all infinities. So in fact, inverting the operator BDX is almost like dividing by 0, and the reason is that the derivative operator doesn't have a unique inverse because there's the arbitrary constant of integration that we haven't specified. And the way we can specify that is by prescribing a boundary condition. So if I go back to my course mesh again, so we can see what's going on. I'll get rid of these derivatives here. Bt full dx. All right, so let's prescribe the very first value of the integral. So the integral will be a function, right? If we apply bdx to a function, we'll get its derivative. And if we apply the inverse to the derivative, we should get back the original function up to an arbitrary constant, and we'll prescribe that constant by prescribing the first value, the x equals 0 value of the integral function, the function that is the antiderivative. All right, so we can do that by taking bdx, and what you notice is that each row of bdx, or what's important to notice, that each row corresponds to a derivative at one point on the mesh. So the first row is the derivative at x equals 0. And so instead of prescribing the derivative at x equals 0, what we will do is we will prescribe the value of the function. And so the first thing we do is we zero out the original bdx matrix by setting it equal to 0. Let's see what happens now. So notice what bdx looks like now. And after I zero out, then bdx or full. Now the first row is all 0. So we've gotten rid of that equation, and then we replace it instead with bdx of 1 comma 1 equals 1. So we make sure that the first element of the first row is a 1. And then what we will do is when we apply the inverse operator to get the antiderivative, we will replace the derivative at the first point by the value of the function, so that then when we invert, the function will be defined everywhere. So let's see what bdx looks like now. Right, full bdx. It is now just a 1 here, and then there's all the finite differences for all the other rows for point x, the first x point, the second, the third. So this is the 0th or the first x point, the second, third, fourth, fifth, and sixth. So it has 6 rows because there are 6 elements on my mesh x. And then the inverse, full of inverse of bdx, now it just looks like a lower triangular matrix of 1s. And so if I was to multiply this matrix by a bunch of values, well, the output, the first output will just be the first function value. The second one will be the sum of the first 2 points, then the sum of the first 3 points, first 4. So it produces the analog of a cumulative sum, which is the discrete analog of an indefinite integral. So, right, this looks a lot like an indefinite integral, and in fact that's what it will be in the limit where I make dx go to 0. Okay, so let's now let's try it out. Let's pick a function. Let's make this smaller, 0.1, and then we'll define our function. F is equal to x cubed. So if we want to take the antiderivative of f cubed, we should get 1/4 times x to the fourth, right? So integral of f analytical is equal to x to the 4th slash 4 plus some constant. And we can decide whatever constant we want. Let's pick the constant to be 10. All right, so this is the integration constant. So if I plug in x equals 0, then this function here should be equal to 10. And so that's going to be the value I must prescribe on the right-hand side. So the right-hand side is equal to f, except for the first point, right-hand side of 1, should be equal to the integration constant, which is 10 in this case. And then I can find the numerical integral, and that should be the e dx backslash for to invert and then I put in the right hand side. Alright, let's run that. e.g. plot x integral analytic in red, hold on, oops, lowercase f, hold on, and then plot x if numerical in blue. And then let's bring up the figure. Oh, I forgot to clear everything. Let me clear the figure. CLF, plot, analytical, hold on, plot, numerical in blue. And now you can see the two functions. Let me make it bigger. Right, not too bad. There is some error, right? It's very small at first. It starts at 10. Right? I don't know if you can see the axis. Let's see, set GCA font size 10 to 16. Right, so the function starts at 10, both the blue, which is the numerical, and the red one, which is the analytical, and then they increase. There's always a bit of an overshoot, an error, which seems to grow, but the relative error is fairly small, so let's plot the relative error. Figure 2, plot IF analytical minus IF numerical divided by IF analytical, and then x and times 100 to get a percentage error. CLF, plot, make them both columns. Column, bring up figure 2. Alright, so this is the relative error, which in percentage, so it's around 0%. It's a perfect fit where I prescribe the initial condition, and then the percentage error grows, but eventually the relative error starts going down. The maximum was around minus 4.5. So let me put this in my script, and then we can increase the mesh resolution and see if our errors decrease. So if I come back here and I plot x 100 times IF analytical minus IF numerical dot slash IF analytical x label x, y label relative error percent. All right, so here we have an error of around between 4 and 5%. If I increase my spacing by a factor of 10, my derivative operator was what's called first order, so presumably my integral operator will also be first order, and therefore my error should be about 10 times smaller, and so we should expect an error of around 0.4 to 0.5%. So let's see if my prediction is right. I haven't tried this yet. e.g. Right, around 0.4 to 0.5. And if I decreased one more time, now it goes down by another factor of 5. So this is an integral rule which is not the most accurate. The trapezoid rule, where we have centered differences, would be much better, would give a more precise answer. But anyways, this is inverting an operator. So we saw, to recap, that when we didn't have the boundary condition, the inverse of the backward difference operator was all infinities, was singular. But when we prescribe the boundary condition, the value of the integrated function at x equals 0, then we can produce a derivative operator which was invertible. And we could, if we want to, for example, just to bring this point home here, if I wanted to change the value of the function, the first value, let's say at minus 10, then I could so minus /4 minus 10, then I would prescribe the right hand side here to be minus 10. And if I run it, now presuming the functions work, now the relative error goes to infinity at x equals 0. That's because I'm dividing the error by, to get the relative error, the value of the function is 0. Sorry, not at minus 10. So should be 40, sorry, 40. 2.5, so around 2.5149 in the middle here, the function, the integral, is equal to 0. The indefinite integral is equal to 0. So when I take the relative error, I'm divided by 0. And that's why the error kind of blows up around this point. That's an unavoidable fact, that it doesn't really make sense to compute the relative error of something, of a function that's very close to 0. We should look at the absolute error at that case. Let's plot x comma if analytical minus if, I need a colon, minus if numerical. And let's do it in figure 1. And it goes from between 0 and minus 0.07, but the value of the function itself, xif numerical, it's a function that ranges from around minus 10 all the way up to around 160 or so. And so that's a pretty small error, the absolute error. Okay, so we can change, the point was, we can change the integrating constant by changing the right-hand side, the first element, where x is equal to 0 in our right-hand side when we apply the inverse of b dx. All right, so that's the idea behind inverting these differential operators. Now we're going to do a two-dimensional case, and what we're going to invert is the Laplace's operator.